Now we are entering data structures. So in this module, module 2, we'll be learning basic data structures, which are like simplistic. So data structures like stacks, queues, linked list. And apart from these three basics data structure, we will be also learning how to analyze efficiency of any algorithm. So today in this class, we'll be discussing fundamentals of analysis of how do you find out the complexity of any algorithm. Or basically, I would say, how would you evaluate if an algorithm that you wrote is good enough or not, or should you improve it further? And this is a very important tool to further understand different algorithms that we will be learning throughout the structure of this course, such as different sorting, searching, all those algorithms, different graph parsing algorithms, different graph shortest path finding algorithms, all those. For each of these algorithms, we just don't want to learn the technique. We want to understand it from why is this better than this. And it's just the practical way of learning. That's how I understand things the best. If I understand what's the important to learn this thing and how would it be better. And that's when I understand that thing in a much better way. And that's why I put this analysis of algorithm right before we jump into those algorithms. So today we are going to discuss this, and the remaining the stacks, queues, and linked list will be over videos. Okay, so analysis of algorithm. Let me do a PowerPoint presentation view. This is much better. Okay. So analysis of algorithm. Why is it important? Where do we use it? And what's the point of learning it? There are different things that we are usually using in our routine life, like Google Maps is one of the best example where we use the core of Google Maps is different graph processing algorithms, where, for example, if you want to reach from this source A to destination B, you would put in these both A and B points, give it to the app, and then it says you what are different routes that are available to you to go from source A to destination B. Different routes have different priorities. Some of the route could be without tolls. Some of the route could be the fastest possible, and some of the route could be by avoiding the traffic or the shortest distance or something like that. So these different priorities could be the weights for those edges that's been connected when this route is found. And how these priorities are designed is again depends upon the efficiency of algorithm, right? The shortest time that the paths that takes me in shortest time from source A to destination B. So shortest time is our priority, and then we want to measure the shortest time as our efficiency of that algorithm. So one thing is definitely whatever is the priority, the time efficiency is the critical concern for anything in our today's world. If we can do anything in 1 minute, why to spend 2 minutes on that, right? So we want everything to be as fast as possible. So one of the issue that we analyze while we analyze the efficiency of algorithm is time efficiency. The second most important issue that we want to analyze is the space efficiency, because sometimes what happens is this algorithms, it takes a lot of memory in the system while processing it. And this is the space that it occupies in order to give the output. And although we have distributed systems, we have systems with huge memory these days, but still this resource is always going to be a limitation. There is a bunch which you can use and you cannot exceed over that. On top of that, this bunch needs to be shared by different algorithms. You just can't say that because you want to find in a Google map, you want to find from source A to destination B, the path for that, shut off everything else. Then your phone operating system wouldn't work. It needs that resource, the CPU, the memory that it has, to be shared by different things that's happening in background and foreground. And that's where the space efficiency is one of the very important thing while we design our algorithms. We want our algorithms to consume as minimum space as possible so that the resources could be used by other things as well. Here you see on top, I have correctness as one of the issue. I assume that's one of the basic, because if your algorithm does not run, there is no way to find anything further than that. So correctness, where it's the minimum basic that whatever you're designing should run and should run without errors. By without errors, I mean both the errors, the compile time errors as well as the runtime errors. Sometimes you find things like segmentation fault, memory leaks, all those runtime errors. Resolving them is as critically important as resolving your compile time errors, because of those runtime errors, sometimes your algorithm might not be doing exactly, although it's running, it's giving some output, but it might not be doing exactly what you wanted to do. Or in some cases of corner test cases, those are the test cases which you have not yet implemented. The algorithm will totally crash or totally give like a different, unexpected, or unuseful output. And resolving each and every runtime error ensures that those things doesn't happen. The last thing, the issue that we will be studying in the analysis of algorithm is optimality. By optimality, we want, okay, so it's a combination. Correctness is mandatory, no negotiations with that. Time efficiency and space efficiency. There is a very fine balance of optimality to be decided between these both. Sometimes, like, you will come across an algorithms, they have very excellent time efficiency, but very worst space efficiency. That's not, it could be depending upon the scenario of where you want to use this algorithm. If you are using it in a test case, like for example, NASA is using this algorithm to launch a rocket, it might want something like this. It might want the best time efficiency, and space efficiency doesn't matter because it will assume that the launching a rocket is a priority task and all the resources that they have is at the disposal of this just one task. So all other tasks are suspended until this is completed. But if you are running some another, if you are run into some another scenario, then in most of the scenarios, time efficiency and space efficiency, both are equally important. So we have to juggle with the managing optimality between both of this. And sometimes your space efficiency is more important because sometimes you really want to, like in IoT, most of the IoT devices, you really want to compute things in, sorry, I just want to go back to our Zoom and check if anybody is waiting. I don't think so. Okay. So in most of the IoT applications, your devices are on the edge, and they are those are the devices that has very few resources. So sometimes you are analyzing some extreme conditions in desert or under oceans, and these are the sensors that collects, and you want to do like on-site compute.
Excuse me. There's a student
Yes.
that wants to join, and you have to let them in.
I see. Okay.
Right.
Go. Thank you. Okay. So where were we? We were at the IoT and the edge devices. So in those devices, the space efficiency is more important because it has, those are the devices that has very limited resources, and you want to do like a lot of things using those very limited resources. So any algorithm that you want to deploy on those devices, you want to be considerate of the space that you're using for those tasks. Now, in order to resolve all these issues of while analyzing the efficiency of any algorithm, usually we have different approaches. One is theoretical approach, which we'll be learning more about it in this class. And the second is empirical approach. In the empirical approach, you validate the results that you got from your theoretical analysis. So basically, an empirical approach, you design the algorithm, you deploy it, you run it, and then you test to see if those repeated results are aligned with how you think the algorithm should behave. Any questions until now in terms of what, before we move on to the theoretical analysis, any questions upon on the use of why do we need to learn or where it's applicable or anything like this?
I have a question.
Sure, go ahead.
So I just want to make sure the empirical analysis is just basically a validation of the theoretical analysis, correct? Based on what you were saying, it's more like a validation to make sure that your results were correct when you implement the algorithm, right? In the theoretical
Yes,
base.
that
Okay.
makes the most sense. So mostly people in a real life, you want to get through your theoretical analysis first because those are easy, and those are based upon the things that you already know. But then the second step, you want to go through the empirical analysis where you want to validate what you know is correct or not. But sometimes in a very complex situations where people have, like, there are situations where people have no clue of how to perform a theoretical analysis. In those scenarios, there are test cases where scientists directly move towards analyzing things empirically, and you have no clue of what the theoretical analysis.
Okay, thank you.
So now moving further into theoretical analysis, the things that we are actually most concerned of is two things. First is you want to know in any algorithm that you're analyzing or that for which you want to know the theoretical complexity, what is the basic operation? So what is that basic compute operation that it is performing? And the second thing is what is the input size that it's working on? So on whole, this input size, on each of this element of input size, it's performing this basic operation. So that's the first step to get the idea of in order to compute the complexity. The actual, what would the basic operation look like? This basic operation could be anything like multiplication, adding, division, subtraction, any of these basic math operations. And the data could be anything like your input data size. It could be your intermediate data set. So you might process the input data set, get some intermediate data, and that intermediate data might be then input to some other operations. But one step at a time. When we start analyzing efficiency of algorithm, we start analyzing one single step. We see what are the operations performed in that step and what is the data that's been worked on in that step. So here, this is an equation where if we want to compute the runtime is the function of input size and the number of times the basic operation is executed. So COP is the execution time for the basic operation or the cost. So basically, everybody knows that in a compute architecture, one operation can take lesser time than the other operation. For example, addition is way simpler than an operation like a division. So it depends upon if you want to theoretically find the runtime of any algorithm that you define, it depends upon that exact execution time for the basic operation for the architecture of compute system that you're working on. It depends upon the input size, and it depends upon the number of basic operations that you are executing in that cycle, which you are evaluating. So let's jump into seeing how would these input size and basic operation look for some of the practical problems. So here we have the list of some of the practical problems. Let's say, for example, if the problem at hand that we are solving is searching for a key in a list of n items. This is a search problem where you have n items. So what's your data set? N, right? Because you are working on n items, that's your input size. What's the basic operation here? The basic operation is key comparison, because while you are searching, You know that this is the item that you want to find. That's searching for a key. Your key is the one that you want to find if it exists in this n sized data set. So you compare this key with each element of this data set, and that's the comparison here becomes your basic operation. In the same way, if we have the problem at hand as multiplication of two matrices, so here the dimension of these matrices, or the total number of elements in the matrices, that will be your input size. But your basic operation here will be multiplication of two numbers, because that's what you are doing for each element in that matrix. Also, there are other examples of checking if the integer n is prime. That is another interesting problem. There again, as we see, checking if the given integer n is prime, n's size, that means the number of digits that the n has, is our data set, because that's what we will be checking. That's what we will be dissecting in our algorithm, and that's what we'll be using. While division is our operation. So here you would be dividing this n number that's given to you with different integers from 1, 2, 3, like that. And then if the division is successful, apart from the number itself and 1, then it is not a prime. That's the basic definition of a prime number, that the prime number is only divisible by 1 and itself. If the division is unsuccessful until you reach that number, for example, number is 49, then you would divide 49 by using 1, 2, 3, all the integers. If the 49 is divisible by anything before 49 itself is reached, then it is not a prime number. Well, 49 is a prime number or not?
No, because divisible by 7 also.
Yes. Okay, this shows that, okay, people are awake. But I do want to hear from even other people apart from Rohan. I see he is being active in this class, but I want everyone else to be as active as him. Then typical graph problem is definitely, we can dissect it into what is an input size. So for a graph, the input size is the number of vertices or the number of edges. Again, it depends on what we are doing in the graph. So here you see I've mentioned and/or. Sometimes just the number of words, depending upon the algorithm that you have designed, sometimes just the number of vertices is enough to analyze the efficiency. But sometimes you want to see these vertices, how densely they are connected. So if the graph is more denser, then processing that graph would be more tougher. For example, if you have to process the LinkedIn graph or the Facebook graph, it depends upon if any person has more number of friends or more number of connections, then analyzing anything about that person might take more time, because then you have to process more number of edges. And sometimes it also, again, depends upon just the edges. Doesn't matter how many vertices you have, but if you have the end-to-end, like if you have overall more number of edges, then it takes more time. So either number of vertices, either number of edges, or both matters when you are analyzing different graphs. And the basic operation that we usually are concerned when we deal with graph is visiting a vertex or traversing the edges, because that's how we process different algorithms. We traverse from we traverse along the edges and we visit different vertices. So those are the two basic operations that we perform. Next, moving on towards a step deeper in our theoretical analysis. After having this basic knowledge of what do we need, why do we need, and how do we use it by using the input size and the basic operations, the next thing we want to know is there are different form of complexities that we want to analyze. Most of the time in this class, we'll be talking about the worst case complexities, that is denoted by big O of n. But I want you to know, before we just jump into the world of worst case complexities, I want you to know that there are different complexities also. Sometimes you might encounter a question in an interview or outside or in anywhere that what is the best case complexity of this, or what is an average case complexity. So by complexity, it doesn't always mean worst case complexity, which we take as assumed once we advance in the subject further. But most of the time we do analyze worst case complexities because that's what we are practically concerned of, right? I mean, if you have designed something, you want to know, okay, in worst case, how much long should I need to wait before I get the output? Very few times you are just concerned about the best case, where you would be like, okay, if I know the best case, that I could be optimistic and I could expect that this thing will get done, or I'll get the results as soon as I reach the best case. So best case and worst case gives you the best possible and worst possible limits of any algorithm. But in between these both, we have average case. And the average case analysis, I think it is way more complex than finding the best case and finding the worst case. And the average case analysis it is definitely not just an average of your best case and the worst case. So it's not best case plus worst case divided by 2. Average case analysis has a different statistical process. And if you are interested, maybe in an extra class or in the office hours, we can go through finding average case complexities of some problem that you have that you're interested in finding. But most of the time we don't use average case unless you are just concerned about the statistical analysis of the issue the most at hand. So not looking at the practical aspect of the problem solving. And so the most important thing for you to remember is average case is not the average of best and the worst. It's a different analysis. But further, we will be more concerned about how do we find the worst case complexities. So in worst case complexity, what we assume is our input size is maximum possible. And the operations that we are dealing with, we want to have like a list of all the operations that we could have encountered in different scenarios. Okay, so what best way to learn rather than exploring it yourself, right? So this is a search problem. Here I have the algorithm for the search problem in which you have to search for element k in this area of 0 to n. And this is the algorithm that's written. So for this particular algorithm, in order to solve the sequential search problem, what would be the worst case complexity? I want you to work on this 3. We'll take a minute off for you to work on these 3, and then we will discuss that. Okay, so does anybody want to speak up? What will be the worst case complexity in this case?
Would the worst case be O of n?
Big O of n, correct?
I think the worst case would be if it's not there at all.
Yeah, so what would be in that case? What would be the complexity in that case? Will it still be big O of n? Thinking, pondering. It helps if it's in the class. I could see the expressions of thinking and pondering on your face and respond accordingly. But I think here we don't have that leverage. So you got to speak up if you are thinking something else. So yes, it's
Oh,
correct. The
so,
worst case
uh,
complexity is, go ahead.
oh no, that big O event just means that it goes through the entire list until it finds the result, right? So if the result isn't there, I mean, it would still be big O event. It just would never find the answer, or would it just like what would it be?
Exactly. So if it doesn't find the k in the string of 0 to n minus 1, which is a string of length n, then it still had to go through all that n things, right? So in that case, your complexity will hit the worst case complexity, which is big O of n. What will be the best case complexity in this case?
Big O of 1?
Someone else. Okay, hold on for the next answer at least.
Sorry.
Big O of 1, yes, it's correct. I just want everybody to participate while we are discussing. So the best case complexity is big O of 1. That's given the case where you find the element right as a first element. So if A of 0 is your element k, if A of 0 is equal to k, that's your best case. You don't have to search anything further. You just return, yes, the element found. Now, the critical question, what is average case complexity in this case? Any guesses? Because we have not discussed how to find the average cases, how to go through the statistical analysis, but what I'm looking for is just a guess. Think logically if this is a problem, and if you run it again and again and again, what would be the average runtime that you find?
N over 2.
N by 2, assuming that the k is always within that string of n. If we consider the case where the k need not be in that string of n things, then it is not n by 2. So this is a very thin line that I want you to understand of how the average cases are concerned. So here you see the best case is 1, the worst case is n. But the average case need not be n by 2 always. It depends upon different scenarios. So average case is equivalent to n by 2, but not exactly equal to n by 2. That's the thing that I want you to remember at this point. Okay, any questions on these analysis from anyone?
When dealing with average case, how often do you have to factor in, like in this case, k not being in the list at all? Like how much is that usually a factor?
It's a big factor. So if the k is not in n, your average, like think logically, even if we don't know the math behind finding average cases, but we can always use our brain to make logical analysis. So let's say if k is not in n, in that case, averagely you will still spend n amount of efforts to go through that. And that's how the effect that this thing is bringing to our average case complexity is definitely non-negligible. Okay, so now let's jump into a bit more complex problems. So here we have 3 representations where we represent the big O of n as worst case. So here we have like 2 functions. So usually any complex equation, we represent it as a function. If the complex equation is with a variable n, we represent it as f of n, g of n, anything. So f and g are just the function representators for that equation. And n shows that, okay, this equation has just one variable and that's n. All other are constants. So here, if we are analyzing the complexity of 2 different functions, then we have, so our one function that we have at hand is the worst case, the average case, and the best case. We represent these things as big O of something, the theta of something. Theta is an average case and omega is the best case. Big O is the worst case, theta is average case, and omega is the best case. Now here there are some examples, some test cases for you to work through. where on the left-hand side, there is the function f of n, and on the right-hand side, it is the complexity analysis. What you have to figure out, or what you have to fill in the blank, is whether it belongs to or it doesn't belong to. So basically, if n, let me do the first one. So if this function n blank, it belongs to or doesn't belongs to big O of n square. So big O of n square is a limit which is higher than the n, and it's considering the worst case scenario. So in this case, because we are considering the worst case is n square, n is below that worst case. Think if it's above, if it's below in that perspective relation. And that's where the answer to the first blank would be belongs to. Because we are considering at worst case, it could be n square, but if the function has a complexity of n, then it belongs to within the boundary of the worst case. I want you to think and fill the belongs to and doesn't belongs to for the other blanks. And again, we'll catch up in a minute. So take your time, fill it. Okay, so what do you think the answer for the second one would be? The equation is 100n plus 5. Does it belongs to or doesn't belongs to the worst case of n square?
I put belongs to.
Belongs to, correct. Excuse me, my mouse is showing like a bit crazy thing. I'm not able to point it. Maybe because of different applications running on my system at this point. But yeah, I'll repeat the answers again and again. Once I'm able to see my mouse, then I'll be writing it there. So yes, so the answer for the second one, which is 100n plus 5, it belongs to big O of n square, same as the first one, because here the variable is n, and n is beneath the n square. And we are looking at the big O, so we are looking at whether it's beneath or not. How about the third one? Someone else. I want each of the answer from a different person.
Belongs to.
Belongs to, correct, Iris. So the third one, it is a bit complex, bit different than the first two, where you have an equation half n minus 1 into n, whether it belongs to or doesn't belongs to the big O of n square. So the left-hand equation, if you resolve it in terms of n, it's a function of n square, because n minus 1 multiplied by n. And function of n square is still within the limit of big O of n square, right? It's still equal to that. So that's where it still belongs to n square. But if, for example, if you had one more n there, or something like n minus 1 into n minus 2 multiplied by n, then it wouldn't be, then it will be it doesn't belongs to. So answers to all first three blanks are belongs to. Let's go to the other one, n square. N
Wait, I
square
have a
blank
question.
big O of n. N cube. Sure. Yeah, go ahead.
As you were saying, if there was a third n in that equation, then it would not have belonged to the big O.
Yes, that's very
Okay.
similar to the fourth blank.
Okay. Okay. Thank you.
Okay, so I guess then we reveal the answer to the fourth blank, which is for n cube, it doesn't belongs to big O of n square, because the curve of n cube is above the worst case complexity of n square. But here again, if it was not big O, but if it was the best case complexity, which is omega, then it would have been belongs to, because when we are looking at omega, we are looking at things if it's above, because remember, omega belongs to the best case. So if the best case is n square, n cube still falls under the best case of n square. So it depends upon which is the function we are looking at. So here, because we are looking at big O, we are looking at if the things are equal or beneath it. So n cube is not equal or beneath it, it's above it, and that's where it doesn't belong to. Answer for the fifth blank should be straightforward. Can I quickly get it, please, from anyone?
Doesn't belong.
Perfect. Yes, and I don't think we need explanation for that. It should be clear. How about the sixth one?
That one either.
Okay, Christine, please hold off your excitement. I'm still waiting for other people to jump onto the discussion. So I know you understood, I know you want to answer, but we need some time to hold on. If nobody answers, then surely we could go ahead. So the sixth one, again, it is doesn't belongs to, because as a cumulative, it's n to the power 4 plus n plus 1, but still the n to the power 4 is a dominating factor there. So this is a function of the order of n to the power 4. And for a function of the order of n to the power 4, the worst case complexity cannot be less than n squared. It will be always either equal to n power 4 or greater than n power 4. So now we move on to the average case analysis. What do you guys think for a of n squared plus b of n plus c? Does it belongs to averagely the theta of n squared? You are perfectly fine speaking up your guesses, so please.
Does it, I think, belongs?
It belongs to, correct, because in average case analysis here, remember, we are not finding exact what is average case complexity. We are just looking at the ballpark. Does it belong or does it doesn't belong? So that's why if the function is of the order of n square, then unless we have n, until we have n square as our average case on the right hand side, it belongs to. The next one?
Doesn't belong?
Doesn't belong, correct, Kevin. So because now, as I just said, that until we have the same order on right hand side and left hand side for the average case complexity, which is theta, then we will have belongs to, but directly in the next case, it's n cubed. So n cube is not exactly the same order of n squared, and that's where it doesn't belong to.
I don't know if you've been, the people are answering in the group chat for the Zoom. If you haven't seen it, just
Yes, thank you for the people who are answering, but while taking, it's just a bit tough to refer to the group chat itself. I do refer it in between now and then, but with this cursor problem, it's being crazy. So I would encourage if you can speak up rather than putting it there.
Professor, I have a quick question.
Sure, Gino. How do I pronounce your name? Gino?
Yeah, Gino, you got it. Yeah.
Okay.
Okay. For the an squared plus bn plus c, if the n squared wasn't squared, if it was just regular a of n, would
Mhm.
it still belong or no?
No, it wouldn't. So
Okay.
for theta of n, it should be exactly the same.
Okay.
So it wouldn't, but if it was big O of n square, big O of n square,
Mm-hmm.
then it would belong.
Okay.
Because for big O of n, we are looking at anything that's smaller or equal to whatever it is within that big O.
Oh, okay. All right. Thank you.
Okay, so last three analysis on omega of n. What are your answers? N cube, does it belongs to omega of n square?
Yeah.
Yeah, it belongs.
Okay, correct. N cube, yes, it does belongs to omega of n square, because for omega, we are looking at something that's above or equal, and n cube is above n square. The second one, which is half n minus 1 multiplied by n, does it belongs to omega of n square?
Doesn't belong.
It does. It's
Oh.
still a function of n square. Your left hand side is still a function of n square, and n square is, remember, above or equal. So n square is equal to n square. So for
It's that when we're doing
big
this, you
O,
ignore the coefficient, right?
we are just finding out the complexity in terms of n. So if
Yeah,
it's half
but
n minus 1 into n, it's a function of n square.
yeah, but what I feel like a lot of people like it's because it's like 1/2, so n squared over 2. But the thing is that you ignore the coefficient in this case, right?
Correct, because all those divided by 2, multiplied by something, added or subtracted by something, these all falls under the constants. So the complexity still remains in term of n. If n is very small, so again, getting back to thinking it logically, think if n is your 5 or 6, then that factor that you have, divide by 2, that matters. But usually when we are analyzing complexity, we are assuming that we are analyzing all the range of n. So unless you have a condition given that n is smaller than this, then you assume that n could be literally anything. N could be 10 million, n could be 10, I mean, it could be anything, any big number. And once you have, for example, if you have 10 million number as n, then that factor of half is literally disappears, doesn't matter. What about the last one, 100n plus 5? Does it belongs to the omega of n square or not?
Doesn't belong.
I
Doesn't.
don't think so.
Doesn't belongs to. I like this chorus answers. Hopefully we have more of those. That kind of shows that, okay, all of you got it correct and all of you are ready to answer it. Okay, so I think we'll move on to the next. Okay. This is crazy with my mouse disappearing. Come on. I'm sorry, it's just how to, I'm figuring out how to go to the next slide with no mouse there. My enter, arrow keys. Okay. Okay, I think it was an annotate which was giving this issue. Okay, so this figure kind of illustrated visually of how you consider big O theta, and omega. As we just said, it's for big O, it should be equal or below. For theta, it should be exactly equal. And for omega, it should be equal or above. For these complexity analysis, there are some properties of asymptotic order of growth, which we would adapt from the general function analysis properties. So here are just few of them, some of the properties that could help as you go along when you analyze different algorithms. Because most of the time what happens is your algorithm is a combination of multiple functions. You analyze the complexity of each individual function, but at the end you want to know the overall cumulative efficiency of the whole algorithm or the complexity of whole algorithm. And that's where these properties of how do you combine different things that comes into picture. So some of the simplistic properties are, again, I think all of you understood the belongs to and doesn't belongs to concept very well. So that's what you use when you are analyzing the complexity or when you are accumulating the complexity of different individual functions into a whole algorithm's complexity analysis. And both this O and omega, they follow the conjecture properties. So if something, so here, for example, if f of n belongs to big O of g of n, where g of n's are the functions that were given in the before slide that we did the exercise, g of n's were the functions that were given inside the operations of big O, theta, omega. So if this is true, then it implies that the g of n will also belong to the omega of f of n. So it has the controverse properties, both. You can exchange both the functions and big O can be replaced with omega. And we have, so if we have this as correct, so if f of n belongs to big O of g of n, and if g of n belongs to big O of h of n, then we say it also implies that f of n belongs to big O of h of n. So it's the property of indirections. If you have something that belongs to something and this second something belongs to something else, that implies that the first thing also belongs to this end thing. And some other properties are like, so if f1 of n belongs to big O of g1 of n, that's one function. There's another function, which is f2 of n, that belongs to big O of g2 of n. Then when you add both of these functions, f1 of n and f2 of n, the complexity is not the addition of big O of g1 of n plus g2 of n. The complexity, rather, because we are considering here big O, so the complexity becomes max of both of these when you are combining. And this is the function that you will be using mostly in analyzing all the algorithms, because you will end up with different functions in the algorithms and you want to add up the complexity of all these functions to have the complexity of your algorithm. So in order to do that, this is the equation that you'll be using. So how would that happen is you would consider the max, big O of max of g1 of n, g2 of n, g3 of n, how many ever functions you have to find the complexity of whole algorithm. Any questions? Okay. So now logically speaking, what do we call as best time complexity and what is the worst time complexity? This table over here could be your reference or your reference at the last page of your book while you are analyzing complexity. Definitely the constant complexity, the best one. That's what we want always in this world, but it doesn't happen, right? If we have constant complexity, what it signifies is irrespective of the problem size, we will exactly get this done in this much time. And nothing could be more better than that constant complexity. The second best is logarithmic complexity, where you have, if the problem is of size n, you can say that, okay, you can do it in big O of log of n. And that's, as you computationally evaluate the value of each of this function, you will know if you draw a log n curve, it is above 1 and it is below the n curve. The third best is n, where the complexity is linear. So you say that, okay, if you have a problem of size 1000, it will take time to run in the order of 1000. If you have a problem of size 1 million, it will take the order of time to run as 1 million. The fourth best complexity, which most of the sorting algorithms do incur to have, is n of log of n. Which is, so n log n is bad than n. So big O of n is better than n log of n, but it's still good than big O of n square. So when you are dealing with something where you have to compare one element with all the other elements, and then you have to pick this one element as one by one as all the other consecutive elements in this array. So basically you have to go through all the items that you have for n square times. Each item is iterated twice, as one time as a comparison for some other element and one time as an element itself. So that would lead to a quadratic complexity of n square. But sometimes there is a smart way of doing such problems or handling such problems by reducing it to the complexity of n log n. And that's where the efficiency of most of the sorting algorithms kicks in. There are other worst complexities. Sometimes we end up, depending upon the problem that we are dealing with, is big O of n cubed to the power n. To the power n is an exponential complexity, which we don't want to end up ever. And factorial is the worst, because in the factorial, you see when a complexity is of the order of factorial, your cost is growing at a n factorial rate compared to when your n is growing. So this is to give you an idea of how different complexity behaves and which one is better than which. So wherever you are, if you are at n cube, you want to be at n square. If you're at n square, you want to be at n log n. You just want to be one step above. And once you reach the constant complexity, that's the best heaven achieved. Again, this is just an example that gives the real life calculations of how would, so if the problem size is 10 squared, then how would these different complexities, log n, linear, logarithmic linear, and log n square, n cubed to the power n, and n factorial. What would be the exact cost of processing this algorithm? So you see here the big difference between 6.6 to compute a problem of 10 square to 9.3 multiplied by 10 to the power 157. That's a huge, huge difference. And that's the order of complexity that we are talking here about. Okay, so this is what I wanted to share with you on how to analyze the complexity, deal with some of the problems that we saw here, some of the problems that we exercised. The floor is open for the questions. If you have any questions on analysis of complexity or anything else.